Welcome to this question on 2D vectors, where we examine somebody trying to paddle across a river. In part 1, they'll paddle directly across the river, ending up horizontally down the river due to the flow. In part 2, the person will adjust their heading so they track directly across the river, meaning they'll end up exactly across from their starting point, as if there was no flow. You're in a boat and want to cross a 40-meter wide river that flows at 3 meters per second due east. You can paddle at 3.33 meters per second. In part 1, we'll solve the problem of you pointing north across the river and paddling. We'll calculate in A, how long it'll take to cross, in B, what your total velocity relative to your starting point will be, and at C, how far downstream from your starting point you will end up. In part 2, we'll examine the question of if you need to end up directly north across the river from your starting point. In part A, we'll examine what heading you need to take to end up directly north across the river, and in part B, we'll calculate how long it'll take to cross at this heading. We start part 1 by making a diagram and listing our variables. The river is 40 meters wide and flows at 3 meters per second due east. You paddle at 3.33 meters per second due north. We can add a compass quickly for clarity, and we can list our variables just so we stay organized throughout the question. So we have the velocity of the river, we'll call it v_riv, which is equal to 3.00 meters per second. We have your velocity, so we'll call this vu, which is equal to 3.33 meters per second. And we have the displacement to cross the river, the distance to cross the river, and we'll call this 40.0 meters. Now we're ready to solve part A, where we're asked how long will it take to cross if we point due north across the river and paddle. The key to this question is to remember that the vector of you crossing and the vector of the river flowing are independent vectors. The only thing that affects how long it will take for you to cross is the velocity at which you're paddling across. Yes, the river will cause you to flow horizontally, but that doesn't come into play. For instance, if you stop paddling, you will just flow horizontally at 3 meters per second. You won't get any closer to crossing. So to calculate how long it takes to cross, the only velocity that matters is the velocity that you have as you're paddling across. There's no acceleration in this question, so we can just use our equation of motion to solve this. And that's V is equal to the displacement divided by the time. If we bring in our numbers here, the velocity we're looking for is the 3.33 meters per second, because this is the only velocity that will affect how long it takes you to cross. So 3.33 meters per second. And this is equal to the displacement, how far you have to go. You have to go 40 meters. And we're solving for how long this will take. So that's our variable we're looking for, t. Because we're looking for t, we need to get t on the top. So we multiply both sides by our variable t. On this side, our t divided by t equals 1, and it cancels out. So we're left with t multiplied by 3.33 meters per second is equal to 40 meters. Our t is multiplying our 3.33 meters per second, so we have to do the opposite to get all alone. So we divide both sides by 3.33 meters per second. On this side, 3.33 divided by 3.33 is equal to 1, leaving us with just t. And on this side, 40 divided by 3.33 equals 12.0 seconds. If we paddle straight across, it will take us 12.0 seconds to reach the other side. So we can add this t here. T is equal to 12.0 seconds. And now we're ready for part B. In part B, we're asked to find what is your total velocity relative to your starting point. Another way to think about this question is what would be the magnitude and the direction that somebody would see you moving if they were in a helicopter looking down at you. So somebody would not just see you going straight across because you'd also be flowing down the river. So you would have a velocity that consisted both of a northern component and an eastern component. So let's start by drawing a triangle of this scenario right here. Your resultant velocity is a combination of your velocity paddling across the river at 3.33 meters per second and the velocity of the river pushing you sideways at 3.0 meters per second. This resultant velocity is the vector between these two vectors. So if we draw this in here, this would be your resultant velocity and the velocity that somebody would see if they were above you watching with a helicopter. So we'll call this VR. This is a right triangle. So we can use the Pythagorean theorem to solve for VR. So we can write it up here. A squared plus b squared is equal to c squared. We can call our VU, our A, our V river, B, and our V resultant C. So this gives us an equation of VU squared plus V riv squared, V of the river squared, is equal to the velocity resultant squared. We add in our numbers. Our velocity of U paddling is 3.33 meters per second. And this is squared. And we add it to the velocity of the river, which is 3.00 meters per second squared. And this equals the velocity resultant squared. 3.33 squared is equal to 11.0889 meters squared per second squared plus 3 squared, which is 9.00 meters squared per second squared, and it's equal to our velocity resultant squared. 11.0889 plus 9 equals 20.0889 meters squared per second squared. It's equal to our velocity resultant squared. And finally, to get the magnitude of the resultant velocity, because our VR is squared, we need to take the square root of both sides. So our square root and our squared here just disappear. So we're left with our velocity resultant, which is equal to the square root of 20.0889, which is 4.48 meters per second. So this is the magnitude of our resultant velocity. But velocity also has an angle or a direction in it. So next we need to find this angle right here so that our velocity can have both a magnitude and a direction. Although we now have our VR here, our VR is equal to 4.48 meters per second. When we're finding this angle, it's always good practice to use the numbers we were given in the equation. So here we have the opposite side and the adjacent side. So the trigonometric function we're going to use is tan. Tan of the angle is equal to opposite over adjacent. Putting in the variables we have in the question, we have tan of the angle is equal to the opposite, which is the velocity of the river, divided by the adjacent, which is your velocity. Putting in the numbers here, we have tan of theta is equal to V river, which is 3.00 meters per second, divided by your velocity, which is 3.33 meters per second. 3 divided by 3.33 gives us, and let's move this up a little bit here, tan theta is equal to 0.9009. Taking the inverse tan of both sides to get theta, we get 42.0 degrees. And now to get the direction, I usually suggest making a small compass on the question. So this angle here that we just found, this is our north and this is our east, south, west. This angle is towards the east from the north. So it's 42 degrees east of north. 42 degrees east of north. We can add this answer to our variables here. The velocity resultant, what we're finding in part B, is equal to 4.48 meters per second at 42.0 degrees east of north. And we're now ready to find part C. In part C, we're asked how far downstream from your starting point will you end up? So we can add this to our diagram here. So as you paddle across, you will be flowing downstream. So we can call this the displacement down for displacement downstream. Your velocity crossing the river does not affect directly how far downstream you end up, because the only thing that affects how far downstream you end up is how fast the river flows and how long you're flowing for. Now, we found out how long it takes you to cross in part A, and this is how long you will flow downstream while you're paddling across. So all we have to do to find out how far downstream we go is take the velocity we're flowing downstream at and multiply it by the time. And we'll see this in our equation of motion. V is equal to d over t. Bringing in our variables here, our velocity is the velocity of the river, because the velocity of the river is the only velocity that affects how far downstream we flow. This is equal to what we're looking for, our displacement down the river. And we divide this by our time, the amount of time we flow for, which is the same as the amount of time it took us to cross in part A. Every second longer we take to cross is a second longer we flow downstream. So this is our crossing time, t. We can now add our numbers. The velocity of the river is 3.00 meters per second, and this is equal to our displacement downriver, what we're looking for, and the amount of time we flow downriver, our 12.0 seconds. Our displacement down the river is being divided by 12 seconds, and the opposite of dividing is multiplying. So to get our displacement down the river all alone, we multiply both sides by 12.0 seconds. On this side, 12.0 seconds divided by 12.0 seconds is just 1, leaving us with our displacement down the river. On this side, 12.0 seconds multiplied by 3.0 seconds equals 36.0 meters. So while we're crossing the river at 3.33 meters per second, it takes us 12 seconds to cross. During these 12 seconds, we flow down the river 36.0 meters. So we can add this to our list of variables here. D down is equal to 36.0 meters. How far downstream from your starting point will you end up? Well, you'll end up on the other side and 36 meters downstream. We're now ready to solve part 2 of this question. In part 2 of this question, we examine a scenario where you want to end up directly north across the river from your starting point. In part A, we find the heading we need to take, and in part B, we find how long it will take to cross at this heading. Let's start by updating our diagram and our variables. Pointing our boat directly across no longer works, because when we point directly across, we flow down the river. So we're going to have to point our boat upriver for part 2 of this question. So let's add our vector upriver here. Our boat still travels at 3.33 meters per second upriver. and we're going to point our boat at an angle theta, which we're going to find. Stacking our vectors tip to tail, we draw the vector of the river out of the tip of the vector of u crossing. So this is the flow of the river. So our resultant velocity here tracks directly across. Let's add that as well. Our red vector here for the river flows at 3.00 meters per second. And our yellow vector here is our velocity resultant. To avoid any confusion, we need to update our variables. So the velocity of the river is still 3.00 meters per second east. Your velocity is still 3.33 meters per second. This time it's going to be at an angle towards the northwest. The displacement of the river, or the width that we're crossing, is still 40 meters. Our time no longer applies. This time is for if we're crossing straight across, so we can get rid of this. Our velocity resultant as well no longer applies because we're going to be tracking due north this time. So we're going to find a new velocity resultant, and our how far we end up downstream doesn't apply as well because this time we're tracking straight across the river. We're going to end up with a displacement downstream of 0. So now we're ready to start solving part A. What heading should we take? Let's start by blowing this diagram up here so it's a little more clear. To find the heading we should take, we can just find the angle theta here in our triangle. And this is a right angle triangle, so we can just use trigonometry. We have the opposite side and we have the hypotenuse, so we can use the sine function to solve for our theta. Sine theta is equal to the opposite side divided by the hypotenuse. Bringing in our variables, we have sine theta is equal to, our opposite side is equal to the velocity of the river, and the hypotenuse is equal to your velocity. And now if we add the numbers we have sine of theta is equal to the velocity of the river, which is 3.00, divided by your velocity, which is 3.33. 3 divided by 3.33 is equal to 0.9009, and this is equal to our sine theta. Now if we take the inverse sine of both sides, we get theta is equal to 64.3 degrees. Again, to find our heading, it's easiest, I find, to add a compass to our diagram. So we have our north, east, south, west. So the heading we take here, this theta here is 64.3 degrees. So our heading is 64.3 degrees towards the west from the north. So 64.3 degrees west of north. 64.3 degrees west of north. So we can add this over here. The heading we take, our theta, is equal to 64.3 degrees west of north. And now we're ready for part B. In part B, we're asked how long will it take to cross at this heading? Well, to find out how long it'll take to cross, we first have to find out how fast we're going, our VR here. Again, this is a right-hand triangle, so we can use the Pythagorean theorem to solve for VR. So we can use a squared plus b squared is equal to c squared to solve for our VR. Bringing in our variables, we need to be a little careful. So when we label our sides here, the velocity of the river we can call A, the velocity resultant we can call B, and this makes your velocity C, the hypotenuse. So A is equal to the velocity of the river squared plus B, which is the velocity resultant, what we're looking for, squared, and this is equal to C, which is your velocity squared. Substituting numbers, the velocity of the river is 3.00 meters per second squared plus VR squared, the variable we're looking for, and this is equal to your velocity, which is 3.33 meters per second squared. 3 squared is 9.00 meters squared per second squared, plus VR squared is equal to 3.33 squared, which is 11.0889 meters squared per second squared. To get our VR squared all alone, we have to subtract 9.00 meters squared per second squared from both sides. So here 9 minus 9 is equal to 0. We're just left with our VR, our resultant velocity squared, and it's equal to 11.0889 minus 9, which is 2.0889 meters squared per second squared. And finally, to get our resultant velocity, we need to take the square root of both sides. So on this side, our square root and our square disappear, leaving us with our resultant velocity, 1.4453 meters per second, and we keep a few extra decimal points to avoid rounding errors. So this is the velocity that a bird or helicopter directly above you would see you cross the river at. So to somebody directly above you, you would not look like you're going at an angle. Although your boat would be pointing this way, you would be crossing directly across. So we can add due north here for the direction. In this question, we're asked how long it will take to cross at this heading. So now we have the velocity resultant you would have at this heading. We know the river's still 40 meters wide. There's no acceleration, so to find the time it would take you to cross at this heading with this resultant velocity, we can simply use our equation of motion. V is equal to d over t. Bringing in our variables, our velocity would be our velocity resultant. Our displacement would be our displacement across the river, our 40 meters. And our time would be what we're looking for. Substituting numbers, our VR is what we just found, 1.4453 meters per second. And this is equal to the width of our river, our displacement across the river, 40.0 meters, divided by the time we're looking for. We need to get our variable of the time to the top. So we multiply both sides by t. So on this side, our t divided by t is equal to 1. And on this side, we're left with t multiplied by 1.4453 meters per second is equal to 40.0 meters. Our variable t is multiplying the 1.4453 meters per second. So to get t all alone, we have to do the opposite of multiply. So we divide both sides by 1.4453 meters per second. Do the same to this side, 1.4453 meters per second. So 1.4453 divided by 1.4453 is equal to 1. This leaves us with just t. And on this side, 40 divided by 1.4453 gives us 27.7 seconds. So how long will it take to cross at this heading? It will take 27.7 seconds. Thank you for watching this 2D vector question on crossing a river. In part 1 of this question, we analyzed what it would be like if you paddled straight across and ended up horizontally downstream due to the flow of the river. In part 2 of this question, we analyzed what heading we'd have to take with our boat so that we tracked our resultant velocity directly across the river and ended up due north from our starting position.